Good afternoon, everyone. Hello. Welcome to this afternoon's lecture with Dr. Ollie Folayan. The design and operations of processes that produce and utilize energy are fundamental aspects of chemical engineering. But with the move towards cleaner energy sources, how will the role of chemical engineers evolve? In this lecture, Dr. Ollie Folayan will discuss the ways in which chemical engineers are offering key solutions to achieving the government's net zero targets, whilst ensuring that energy needs continue to be met. From the utilisation of carbon capture technologies to the progressive replacement of fossil fuels and the introduction of renewable energy sources and alternative carbon feeds. Ollie Folayan is a chartered chemical engineer working in the energy industry and co-founder of AFBE-UK. Ollie graduated with a BEng in Chemical Process Engineering with Food Technology from the University of Sheffield in 1999, and then earned a PhD in Fuels and Combustion from the University of Leeds in 2002, authoring 5 international publications in the field of combustion and engineering during that time. To date, Ollie has worked on major CAPEX front engineering designs, detailed design and commissioning projects. In 2018, Ollie was accepted into the Fellowship of the Institute of Chemical Engineering. I think this is going to be a really exciting lecture, so if we can welcome to the stage Dr. Ollie Folayan.
Thank you very much, Ema. And really nice to meet you all. I think, thank you for your welcoming applause. But I think you guys deserve a round of applause for yourselves because you kind of spent this time to invest in yourself. So I'm going to be giving you guys a round of applause. I think you deserve one as well. So yes, as Ema said, I'm a chemical engineer. I am also a co-founder of an organization that seeks to help people into the engineering profession. And the reason is that there are many studies that show that our sector doesn't have a large number of people, particularly from female and people from black and minority ethnic backgrounds. And so we do a lot of work on that. But my aim today is to tell you a little bit about my job, but also talk about the energy transition. So many of you would have heard, let me just do a test here. Is there anyone here who would like to tell me what comes to mind when they think of chemical engineering? So I'd just like a brave volunteer to very quickly tell me briefly what they think of when they think of chemical engineering. What is it? That's good. That's good. That's good. Excellent. Thank you for that. What about energy transition? If I said energy transition, what does that mean to you? Excellent, excellent. And I like the fact that you stuck with the word transition, because that is exactly what it is. In fact, what I'm going to do is I have a couple of polls that we'd set up for you. So I want to get a sense. So would you be able to bring the poll up? Let me know when. Oh, this. How many engineers does it take to work this out? Maybe you come and show me. We'll get started. I'll start with the rest of it and we'll come to the poll. Oh yeah, there you go, there you go. So first question for you is this. Is chemical engineering helpful for climate change? So when you think about climate change and you think about what chemical engineers do you think that chemical engineers can play a role? I want to get a sense of where you are. So, yes? So who thinks it is helpful? Who thinks it isn't? Who's not so sure? One person. Excellent. Oh, well, 24 out of 24 answered yes. Brilliant. So just to tell you a little bit about myself, as Ema said, I'm a chemical engineer and combustion specialist. I've put this picture here, the picture at the bottom right here. That was me it was actually, I just turned 10. But it was just shortly before that I decided I wanted to be a chemical engineer. And the reason I wanted to be a chemical engineer is that I read a book. It was a fiction book. And it was a book about an evil genius. This is true. I'm telling you the truth here. It was a book about an evil genius who could do a lot of really powerful things. And I remember sitting with my dad, and he was an engineer. And so I asked him, how many chemicals do engineers make? And he said, any chemical. And that was actually what made me decide, yes, I'm going to be a chemical engineer. I was also very, very fascinated with fire and flames. And don't worry, I didn't go around throwing flames at people's houses. But I was interested in fire. And so I ended up doing a PhD in combustion. And I once said that in an airport and almost got into trouble. So I'd advise you, if you've got anything to do with combustion, don't tell anyone at an airport. I've worked on various projects, and the projects that I've worked on are in all parts of the world. I'm also a father and a husband. I'd also like to show you, this is one of the projects I've worked on, and the reason I've actually picked this project I was working on, this was in Glen Mavis in Scotland in 2006, and I deliberately picked this particular one because we had a multivariant team. There were so many people from every part of the world. We called it the United Nations because our team had so many people, and everyone was playing a part to making this gas system work. So that's where we are. Now, the reason that what you guys are doing here and the discussions that we're having here is so important is that there are a number of problems. We are living at a time when there are a number of challenges and the world has become so much more aware of the challenges that we're facing. And, you know, a lot of that can be encapsulated in the United Nations Sustainable Development Goals. It's got 17 goals, and I've split them into these areas here: power and health, education, equality, environmental sustainable goals, and energy, housing, and resources. If I was to actually look at any of those, engineers, in many ways, play a vital role in making them happen. One of my, I've heard two favorite quotes that I've heard about the role of engineers in this time. It says, engineers are custodians of the past and the creators of the future. And another one that is particularly relevant to this talk is the one that says, scientists study the world as it is, engineers create the world as it has never been. And that, in many ways, is the purpose of the conversation. So if you can think about it in this sense, that you have, you know, if you think of any of the needs that we're talking about, whether it's housing, whether it's health, whatever it might be, you have a group of people who have been looking at these concepts, studying them for a very long time. And then you have the link between those who actually make those things happen, and engineers play that major role. So think about any societal problem that we've got today. Somewhere in there, there is an engineer playing a huge part of the solution. And that brings us to chemical engineering. Chemical engineering is primarily about taking raw materials and converting them into useful resources that benefit people and benefit society. And the aim is to ensure that it is safe, that is environmentally friendly, and that it is done in the cheapest possible way, or in the most cost-effective way. And that really sums up everything that I've been doing as a chemical engineer for close to 20 years. I'm going to ask you a question in a minute about the difference between, because there's another group of people that actually do the same thing, who take raw materials and convert them into items that everybody uses every day. Can anyone tell me who those are? So they take raw materials, they take it through a process, and then convert it to things that we use every day. Any guess? That's right, very good, chemists. So I'm going to ask you in a minute what you think the difference is between chemists and chemical engineers. But before we do that, I'm going to take you through another poll here, which is, I'd like you to tell me which one's the odd one out. First thing, can you guys shout out to me who these people are? So I'm going to point to the first one. Who's that? Thank you. Who is this? You haven't been watching your movies, have you? Cindy Crawford? That's Cindy Crawford. Who's this? Oh, good. I'm glad somebody knows. And surely, you guys know. I don't want you to tell me his movie name. I want you to tell me his actual name. Thank you. I bet no one will know this one because you're all very young. Who's this? He's acted as a baddie in movies. Well, his name is Dolph Lundgren, and he's acted in quite a number of the Bond movies. He's a very good villain in movies. And who is this? Her name is Mae Jemison, and she was actually a chemical engineer and a doctor, and she was also the first African-American, actually first black person to go into space. And so we use her a lot in our STEM programs, and she's also acted in movies like Star Trek, so she's quite famous. So now that you know, I've actually given you a bit of a clue to what the answer will be here, but can you spot the odd one out? So I'm going to go over again. We've got this guy who's the president of China. We've got this person who's an actress and a model. Actress, 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 scientist and actress. Who's the odd one? Go on. Oh, they're all scientists. They're all engineers and scientists. So who's the odd one out? This is meant to be awkward, guys. This was just meant to give you a hard time. I'm really mean, so I'd like to ask tough questions. Okay, I'm going to give you another clue. This person featured in the 2012 London Olympics. Yes, that's right, yes. So, Ron Atkinson. Now, do you know why he is the odd one out? Because he is the only person here who studied a different field of engineering. He studied electrical engineering. Most people don't know, Ron Atkinson actually did a bachelor's and a master's in electrical engineering before going to comedy. See, Korean engineering prepares you for anything. But everybody else here at some point studied chemical engineering. And that's what I was going to tell you about them. So next question. Oh, I've given you the answer. I hope you didn't see that. What's the difference between a chemist and a chemical engineer? Go on. You are almost there. I'm going to be mean, and I'm going to say you're almost there, not quite. Anyone else want to try? Go on, man at the back. Yes, that's a very, very good answer. So I'm going to leave room for just one more person just to try to see if somebody else can come up with a different take. Interesting take. The main difference, and you know, there is a bit of it in what you said and what the gentleman, what you just said. The main difference between a chemist and a chemical engineer is to do with scale. So you can take any experiment in the lab, you can get those experiments successful. The moment you decide that this is something that needs to go commercial and needs to reach a number of people, you're then talking about scale. How do we scale this up to ensure that you can achieve it? And so the difference between a chemist and a chemical engineer is that chemical engineers scale things up. So as we say here, the difference between chemistry and chemical engineering has to do with originality and scale. Chemists are more likely to develop novel materials and processes. Engineers are more likely to take these materials and upscale them to make them larger or more efficient. So you can think of various activities, whether it's the distillation columns, for example. Those started off as a very, very interesting way of separating water from substances. You scale that up, and you can put it in a refinery, and you can take crude oil, and you can convert it to all of the various ways. So chemical engineering involves converting those raw materials, and it involves scaling things up. So I want you to think about that when we are thinking about the various solutions. Because one thing you will hear very often when people talk about the solutions for climate change and ways of ensuring that we reduce our CO2 emissions, you will hear a lot of people talk about the fact that there was this experiment done in some place that was very successful, and therefore we do have a solution. But the process of getting anything from the point at which the chemist deals with it to a point of getting it to the point where it can actually be made commercial is a massive process. And there are many steps, ways of making sure that this is an experiment that works, that it doesn't have any side effects, that it doesn't create any toxic byproducts, or that if it does, that we have ways of separating them, or ways of ensuring that those tests are successful, ensuring that there is a commercial case for this, because obviously if you cannot sell it, then you can't move it. And so the distance between where you come up with an idea and that idea becoming commercial is a massive one. And that's one that is very important to think about. So take any idea. You typically start with a concept phase. Somebody comes up with something. They think of, oh, I wonder if we could do this. So for example, there is a system called selective non-catalytic reduction. And we use that by linking up urea with nitrogen oxides, and we reduce the nitrogen oxides. So we know that that chemistry works. And then we've also got another system of reducing nitrogen oxides, which is called fuel staging. And we know, for example, that the selective non-catalytic reduction can give you about 30% reduction in nitrogen oxides. We also know that this system of fuel staging gives you another 40%. So somebody says, I wonder what will happen if you bring those two things together. That's a concept. They then come up with exactly what the chemistry would look like, and that's a formulation. You then start to carry out, at a very small scale, these tests. And at the point at which you've done them to such a point that you understand the parameters of this test, you understand the boundaries of it, you understand when it doesn't work, you call that a proof of concept. You then go on to a lab scale, and at this point, by the time you're successful at this point, somebody thinks, ooh, maybe we discovered something here. Maybe we've got something that could be commercial. So I'll tell you what we'll do. We'll come up with a pilot plant, maybe something with a similar temperature profile to what you would get in a commercial case. Let's create that in a lab somewhere, and let's carry out those experiments, and let's see if it works. And then we'll publish some papers, and other people will comment on it. They will raise questions on it. It's a very rigorous process. And then at some point, when that's successful, you might have a company that says, we're really thinking of ways of reducing nitrogen oxides. So we're going to use one of our actual plants, and we're going to let you come and do this experiment on one of our actual plants. And we'll call that a demonstration. So very often you'll hear that, oh, you've got this CO2 reducing technology, and it was successful at Shell, and it was successful at Longanet Refinery. And everyone will say, well, what's the problem then? Why aren't we doing it? Well, you've only really demonstrated it. You haven't done the commercial bit. And then you get to that point. So as you can see, there is a very long process of going from a concept to commercial. So the next time somebody says to you, we've got this technology that is basically the answer to climate change, I want you to ask them this question. What stage in this process is that technology? And I want you now to think about all of the various ways of reducing carbon capture technology. Every one of them is somewhere along these lines. And at the moment, very few of those are actually at the demonstration stage, and even fewer are at commercial stage. So that's kind of where we are. And so the next question I was going to ask you, so this is going to the poll again. So this poll question has to do with the energy transition, and it has to do with the process. So I'm going to wait till I see it in my screen because I jumped the gun the last time. So should we switch from fossil fuel to renewable energy directly and immediately? Or do you think that that process ought to be gradual? So who thinks we ought to be brave and we ought to just go for an actual switch? And who thinks it ought to be gradual? So if you're an immediate sort of person, I'd like you to raise your hand up. Great, fantastic. I can see someone doing that. You have to choose a side. You can't. You're going to be a politician, I think, when you grow up. So who thinks it's going to be a gradual? So more of you think it's going to be gradual. And he's still waving his hands. And now, would anyone like to just tell me, people who are immediate, maybe tell me why you think it ought to be immediate? I can guess why, but can somebody tell me? Someone who thought it should be. Yeah.
The time for waiting until a transition has passed many years ago. We need to get into it now.
Absolutely. Great, good. Were you going to add to the first or the second? Yeah, go on, add to the first one. Yeah, there is a policy framework aspect to this as well, and that should not be ignored. Who thinks it's going to be gradual? I'd just like to know what you think. Lady here. That's right. That's right. You were indecisive, so I'm going to go for somebody else for now. I'll come back to you, don't worry. Yeah, and you? Yeah, that's a very, very interesting. I'm going to come back to you now because I'm not going to be that mean to you. So I'll let you know. Like to hear what you think. That's right. There was somebody else at the back who raised a point, yeah, who was going to make a comment. Or did I ignore someone? No. Thank you. But you've all made very powerful points and actually equally important points. You can have all the technology, getting to a point where you prove it, and proving every context is one thing. The other thing is, you're very right about the sort of policy aspect of this, and the fact that sometimes you do get the issue of vested interests holding up that process as well, and you do need to recognize a recognition of both is really the ideal solution. But this is where I come to what. So I mentioned that specifically just to show you the process of which ideas get from concept to a commercial stage. Yes, we'll have a look at the poll at the end. But if I'm to tell you what I do on a daily basis and the kind of jobs that I do, I'm involved with process design. So that's taking everything from sizing a pipe and taking the principles of Bernoulli's theorem of fluids and taking principles of the conservation of mass, conservation of energy. I'm involved in applying that to everything that you see. So particularly whether it's power stations, refineries, offshore systems, I'm involved in process design. I'm involved in taking all of those principles of fluid dynamics and thermodynamics and applying them to actually either designing things or checking things. Because sometimes what happens is that you might have a system that's been around for a long time. In order to keep that system sustained, you then need to come up with some debottlenecking. You may need to come up with some innovative ways of ensuring that it can be used, it continue to be used, and that's where the analysis comes in. I'm involved in the operation of plant, and that can be very interesting. I'm involved in safety and hazard assessments, because everything that gets done gets put through quite a number of rigorous safety exercises, because as many of you will know, how many of you have heard of Piper Alpha, the Piper Alpha disaster? So that happened in the North Sea and led to a lot of deaths of people. And the energy sector has learned a lot from that, and that influences the way that we carry out our work. I'm involved in process simulation, and so I would use tools, like we have a tool called LIYSF, where you basically simulate the whole system and you carry out calculations, and you can actually do a lot more than you could otherwise do with manual calculations. If you have a system, part of what you've got to do is you've got to make sure it's the right conditions. You've got to make sure that the materials you choose are the right ones, but you've also got to make sure that it's controlled adequately. And so we've got something called process control. I'm involved in commissioning of plant, because what happens is when you take an idea from the sort of concept stage to the point of actually making it happen on a plant, you have to do a commissioning process, and I'm involved in research and development. So if I was to describe a day in the life of an engineer, it could be any one of those things. And one of the things that I like most, that I enjoy most about being an engineer, is the fact that you can actually start with a concept, you can start with an idea, you can build on that idea. You then get to a point where you actually have to implement this, where you have to install it and you have to make it work. And every now and then you get this problem where your theory, what you thought it was going to be, doesn't quite match what's happening in practice. And the process of which you kind of bridge that gap between what we thought it was going to be and what it is, that process by which I surround myself by a multidisciplinary team, and we all kind of try and work out how we get to a solution. That, for me, is one of the most interesting things about being an engineer, because you solve a number of problems. Right, next question for you. I would like you to tell me, now that you're all experts in chemical engineering, you all know what chemical engineers do, can you tell me which of these engineers, which of these companies, does not employ chemical engineers? So you got GlaxoSmithKline Pharmaceuticals, you've got Procter & Gamble, and you can see all the products that they make. This is just a nondescript renewables type system. You've got L'Oreal, and you all know who that is. I was going to say because you're worth it, but maybe that's not good. You all know Shell, and you've all got computers, you know Intel. So which one of these companies does not employ chemical engineers? Go on. Oh, that's a different answer to what I've got in the past. Okay, anyone else want to try? Intel? Most people say Intel. Any other guess? Solar panels? Go on. Shell? So let me give you the answer, and it was a trick question, because all of them employ chemical engineers. Most people usually say, so basically for L'Oreal, that's pretty straightforward. You have a number of solvents that are made in order to actually make the products that they make. And the people that actually ensure that that process works, that it's safe, that it delivers exactly what you want, are chemical process engineers. Anywhere there's a process, you will get a process engineer. We're usually called process engineers, chemical engineers. And Intel, that's usually the one that surprises people. But yes, they do employ chemical engineers, because you have to make semiconductors. And as you know, you've got conductors, the transfer electricity, you've got non-conductors, and then you've got semiconductors that have to be heated in order to become transfers of electricity. And the people that make those are chemical engineers. So all of these companies actually employ chemical engineers. The kind of tasks that I'm involved in process flow diagrams. So if we've made a decision, we're going to produce this solvent that's going to be used for L'Oreal, and we decided this is how it's going to happen. Somebody then provides a sketch and provides an idea of how that process would be controlled in order to give you the end product. And that's a process flow diagram. And I'll show you an example of that in a minute. You've also got heat and material balance, or heat and mass balance. And again, I'm going to show you another example of that. But basically what that says is, how do we account for what's going in through the system? So you have a number of materials that go into this box we're calling our plant, and we've got some things that are coming out. And what governs that is the law of conservation of mass. So we know that mass going in is going to be mass going out, unless we've got a chemical process, and we've got to discuss that. But yeah, generally, that's how you would look at it. And the way we account for that is through a heat and mass balance. We've got the line sizing, as I mentioned before, or you size a vessel. If you are going to, you never design something without knowing how much you're going to design it for. So it's almost a bit like, you know, you were going to have a few friends round and you're about to cook a meal. You would generally think about how many people are coming around. And it's in the same way that chemical engineers think, what size of vessel do I need in order to provide this product? And we've got something called a hazard and operability study. And that's when I've looked at my system, when I've designed it, I'm starting to look at the system, and I'm starting to ask the question, what can go wrong? And I look at various ways in which this can go wrong, and I try to address that. So that's what chemical engineers do. So that's a typical chemical engineering task. Now, I mentioned process flow diagrams. Well, usually a precursor to a process flow diagram is a schematic. So what you're looking at here is simply a distillation system. It's taking crude and it's converting it to various products, and it's using different systems in order to achieve that. And that is a process system. A process flow diagram is far more detailed. So this is taking just one part of it, and it's looking at that unit. So previously, you had a distillation column there, but you get the impression that that's all there is to it, until you look at the next thing, and you see that actually, you do have this whole system of control, of heating, of pumps around the same system. So we look at it in a little bit of detail. I also mentioned heat and mass balances, or mass and energy balances. And I said that that was controlled by the rules of conservation of mass and energy. And that's one of the key activities that chemical engineers do. So we're going to do one exercise now, and I'll see how well you do at this, just to give you an example of what it's like to be a chemical engineer for a day. And you can tell everyone after this that you're now a chemical engineer. So here's a problem, a simple task we got here. We have a system, might be a distillation column, might be a separator of some sort. But what we are doing is we are putting two products into the system, and that is leading to some gas coming out of the top, and it's also leading to some liquids coming out of the bottom of this system. You have some information already, so you know, for example, that for this stream here, M1, you know exactly what the composition is. You know that that is 3% by weight. You know that that is 0.97%. You know that you've got three products, A, B, and C. And you also know what this flow is. So that's what you know in terms of the inlet. In terms of the products, you also have a bit of information. You know, for example, that what's in M is 1% by weight. So, sorry, 100% by weight, because it's 1. And we know that it only contains one of the three products. We know what the flow rate is of this stream, and we also know what the composition is of this stream. So I want you to give me an idea now. If I was going to solve this problem, my problem is to find out what the unknowns are. How would you go about it? So I'm going to get your ideas. I want you to teach me now. So if we were going to solve this particular issue, how are we going to find the unknowns? So what's the first thing that you'll do? Any takers? Oops. Yeah, I'll go with you. Yep, yep. That's a very good approach, and that's exactly what you would do. So the first thing you will do is that you will actually find out, you do something called a degree of freedom analysis, and you kind of touched on that in the explanation that you've just given. You basically find out the number of unknowns. So would you guys like to just read out to me very quickly, what are the unknowns in this, on this picture? Just call them out. M1, so that's your mass flow rate. Okay, next one. Yes, next one. Yep. Yes. A, B, and C as well. Well, actually, we do know A, B, and C because remember, A, B, and C are actually our products. So we haven't called it methane or methane or anything, but we do know what those are. But how many unknowns have you counted then? How many? 5. So we've got 5 unknowns. Now, the next thing we've got to do is find out how many relationships we've got here. So if you like, you could call them the knowns. How many relations do we have here? I'm going to give you a clue. The relationships are there with the fact that you've got A's here, and you've got A's here, you've got B's here, and you've got B's there, and you've got C's here, and you've got C's there. So how many relationships have we got? 3. So you've got 5 unknowns, you've got 3 relationships. What you do is you subtract the relationships, the knowns, from the unknowns, and that gives you your degrees of freedom. So how many degrees of freedom do we have? 2, that's right. So the degrees of freedom is what tells you what other information you need to seek. So right now we know that we have 5 unknowns, we've got 3 relationships, and we know that we've got 2 degrees of freedom. But those degrees of freedom need to be 0 in order for this to be solved. So at this point, you'd reach out to the books, reach out to the client, whoever that might be. And that person then tells you, and I'm going to read it out to you, that M3 is half of the flow rate of M1. And also tells you that 90% of product C is actually down here in M5. So you now have 5 unknowns, 3 relationships, and 2 additional facts that I've just given you. So where does that leave your degrees of freedom? 0. So the system is now solvable. So what I'm going to ask you at some point, let's see who can multitask here, who can basically solve that problem that I've just given you. And who can solve that problem, and who can tell me what the unknowns are, based on the fact that we now have 0 degrees of freedom. Who can tell me what the unknowns are? And whoever can do that, we're gonna find a way to get that person a prize. So whoever can do that first. So I'm gonna carry on with the rest of the presentation. And before I do that though, because I'm nice, I'm gonna give you a few clues. So the first relationship we mentioned is, or the first equation that you've got here is M1 plus 5,300 kilograms an hour is equal to M3 plus 1,200 plus M5. So that's the first thing. So that's the conservation of mass in application. You've also got the same if you're looking at each of these products. So we know, for example, because this is not a chemical system, it's physical. So we know, for example, that all of A is equal to all of A in the products. All of B, so that's 0.03 of M, actually 0.0003, because don't forget, these are all percentages. 0.0003 of M1 plus X2 of 5,300 kilograms an hour is equal to your B in the product. So 0.3 minus X4 times 1,200 and 0.6 of M5. So that's just for B. You've got a similar thing going on for C. So for C, you've got 0.97 of C. So 0.97, sorry, of M1 is equal to X4 of 1,200 kilograms an hour plus 0.0004. So that's basically treat this as a percentage and divide that over 100 times M5. And then you've got the same for C. So I've just given you 3 equations, and you've got 2 clues. M3 is half of the flow rate of M1. 90% of C in M1 is actually here in M5. So you've just got to work those out, and anyone who can come up with an answer that's close to the answer will win a prize. But I'm going to stop there because ideally I would like to have taken you a little bit further, but I'm conscious that we may not get enough time. So if any of you can solve that for me first, whoever gets it first will win a prize of some sort. But that's the process. So that's the process that we've just been through. So let me just go through very quickly what I've just been talking about so far, just so that you've got a good idea of where we are. So I started off with talking about some of the sustainable goals we have in this world, and I tried to define the role that engineers play in it. And then I've taken a step back and actually looked at not just engineering as a whole, but I've looked specifically at chemical engineering and why what we do is so important. The main thing I've said here is that the difference between a chemical engineer and a chemist is that we're the ones who actually take those concepts that chemists come up with, and we come up with solutions. And we do that by scaling things up. So here are a few other examples of things that chemical engineers do. So we have a process called absorption, and it's a form of ensuring that if you have gas that has a high amount of sulfur in it, it might have sulfur, it might have mercaptans, but sulfur, who can tell me why sulfur is dangerous? Why is it important that we do not have high amounts of sulfur in our gas? What was that? It's toxic. It's toxic. So why is it toxic? Yes, which is bad environmentally. Someone else at the back? Oh, so sorry. Would you mind saying that again? Right. I didn't fully pick that up, but yes. One of the main reasons why we don't want it is the reasons that you've mentioned, but it's also the fact that it's corrosive. So you can have sites, for example, where you've had them running for a long time, and if they're running with this sour material, over time they will thicken the walls of your vessels and your piping, and potentially will lead to a disastrous event happening. So it's bad from a safety point of view, it's bad from an environmental point of view. So generally what we try to do is we try and get rid of the sulfur. And this is one of the ways in which we do it. So we come up with a vessel, a bit like the one that we have here, called an absorber. And what we do is we run an agent through it. And that runs continuously. So you have a liquid amine reagent, or it could be something like urea, and that gets run through these absorbers, and that contacts the sulfur that is in here, and it selectively picks it out. So it selectively removes the content that you don't want. And there are different ways of doing that. So some of those systems operate just like this. They operate like an absorber, and they get passed on. And we also come up with ways of ensuring that that's sustainable. So absorption is one of the important ways, and it's basically a link between gas and liquid. So when you have a system in which you are using a liquid to selectively remove a certain undesired component within a gas stream, we refer to that as absorption. So that's one of the processes that we work on. Another process that we work on is something called adsorption. And adsorption refers to using a solid material. So just before the lockdown, I was working on a project. And it was a project because the company I was doing this work for had identified a huge gas stream. It was a huge gas stream that was going to be transferred into a site called St. Fergus. And from St. Fergus was going to be transferred into users all over the country. And, but what they found was that that gas stream had high amounts of mercury in it. And obviously you can't take that into people's houses. So what we did instead is we created something that we put at the front end so that as soon as the gas comes into this plant, it comes in contact with this system. And what this system is that it has a number of items. We call them molecular sieves. And they're just like these pieces, they look a bit like beads. And what they do is they're like beads that have a number of pores in them. And those pores are about the right size for the molecules of the system that we're trying to get rid of. So we found the appropriate molecular sieve for mercury, and they were able to take those out of the system. And then you get your cleaner gas. So that's an adsorption. So if anyone asks you, what is the difference between an absorber and an adsorber, what is that difference? I want to see who's been listening. So what's the difference between an absorption process and an adsorption process? Anyone? Correct. That's right, that's right. So with an absorber, what you're doing is you're taking a liquid system, you're putting that in, it's selectively removing the item you want to get rid of. With an adsorber, what you have is something that is basically located in the vessel, doesn't really move much, and you're putting that through. Do you know one place that you have a similar system is with your catalytic converters in your car? So most of you will have, in your car, you probably use the AdBlue solution, and that's an amine-based reagent, and that's used to get rid of any NOx, especially if you drive a diesel car. So that's a similar system. But the impact of the things that we do, the impact of the operations that we work in, has created concerns amongst a lot of people. It's created concerns because generally these are all reminders of the systems that are also contributing massive amounts of CO2 into the environment. So the question that a lot of people are asking is, I've just gone through a description of what a chemical engineer does. How does this fit in to the world that we're trying to get to, which is one in which we eventually move into much more renewable sources, a higher percentage of renewable sources? How do we meet some of the requirements that have been made by the IPCC? And I've got a quiz coming up on the IPCC and on some of those issues. How do we do that? Well, we do it through something called the energy transition. So we said the energy transition is a pathway towards transformation of the global energy sector from fossil fuel-based to zero carbon by the second half of this century. At its heart is the need to reduce energy-related CO2 emissions and to limit climate change. What are we actually trying to get rid of? Well, usually the carbon emissions that we're getting rid of are usually classified as they're usually put in three categories. So you've got direct combustion, so you've got a system that's burning fuel, putting that CO2 into the atmosphere. We refer to those as scope 1. You may then have a system that is simply purchased electricity, and we've got the emissions that are linked with that, and we refer to those as scope 2. But then all of the polymers, all of the items that are created as a result of these processes are also coming into products and processes that you and I use every day. And those still matter. So that's in terms of emissions. So every time you hear about a company saying, we've reduced our emissions by 90%, very often they may be referring to scope 1, but you've also got the downward impact of their activities. And those are the questions we should be asking them and holding them accountable. Right, so just because I've been bombarding you with lots of stuff and I don't want to give you death by PowerPoint, so I'm going to ask you a few more questions. Question 1, which celebrity got arrested on the steps of US Capitol building in late 2019 during a climate process and said they were inspired by Greta Thunberg? Anyone want to guess? Okay. An age range. Well, let's put it this way: they're not young. They're probably over 50. No. Okay. Yes, very good, very good. That's it. Next question, which 5-year period was the warmest on record? Was it 2001 to 2005, 2006 to 2010, 2011 to 2015, or 2016 to 2020? Very good, very good. So basically, this highlights the fact that, yes, this has become, not just something that a few activists are involved in. It's actually one of the issues that are happening. So I've been asked to just repeat the answers so that people online can hear that. So the first answer was Jane Fonda, the actress, and the second was 2016 to 2020 was the warmest 5-year period on record. So I use these two questions to highlight these 2 points. One, that this is now something that everyone's talking about, and 2, that this is an issue that is real, that is imminent. Because do you want to know before 2016, 2020, do you want to know what was the warmest on record? So before 2016, what was the warmest? 2015. That's right, 2011 to 2015. So it just shows that this is a very serious problem, and it's one that we need to address. But the problem we have here is that we do have a scenario where we do need to get to that point. We do need to get to a point where the emissions that are released, particularly CO2 emissions, are minimized sufficiently enough to ensure that we are somewhere around 2 degrees lower than pre-industrial levels. But every integrated assessment model that has looked at this has indicated very clearly, very strongly, that unless we incorporate a certain element of carbon capture, that there is no way we are going to reach those targets. So this is considering, and part of the reason for that is a discussion we were having before, because there are a lot of technologies out there, and there are actually many governments driving this very strongly now. But even with that, we still only have less than 40 successful carbon capture demonstrations around the world, even at this stage. And remember, I said demonstration, not commercial. And only about 17 of those projects are actually ones that are commercial. And most of them are linked with enhanced oil recovery. So whatever model it is you're looking at, there is no way of achieving this that does not involve some form of carbon capture, and therefore does not involve engineers, and particularly chemical engineers. So bearing that in mind, what is the role of chemical engineers in this particular stage? What is our role? Because the energy transition is about a number of things. It's, as much as you and I would want us to move to a stage where we switch completely to renewable sources, as has been mentioned before, that is not a realistic picture. For various reasons, the technologies particularly, many of them are not developed to that stage, and the commercial value of them proven up to a stage where they can be relied on fully. And also, you have a number of industries, such as shipping, for example, that will still rely on the use of fuels like diesel. And thirdly, the fuel that we get out of the ground isn't just used for transport. It's also being used for, as a source material for various products, for various polymers. In fact, if you look around you, there are very few things that you will see that have been done without the involvement in some way or other of fossil fuels. So it is something that we are going to live with for some time. That said, that's no reason why we shouldn't be, there is no reason why we shouldn't be accelerating and expediting some of the solutions and making sure that they work. So in terms of the energy transition, what does that actually mean for us? Well, it means the gradual reduction of oil production and the use of gas as a more interim fuel. It means companies investing in more renewable energy solutions. It means investing in nature-based solutions, such as forests and wetlands. It involves increasing carbon capture, ending the routine flaring of gas, and reducing methane intensity to below 0.2%. And we can do that by ensuring better efficiency in the way that we measure. So for a chemical engineer, that means two things. It means that we need to come up with a set of solutions that affect these two areas. So some solutions are more digital. They're more numbers-based. They have to do with ensuring that you reduce the amount of human interface. Because if any of us was going to travel offshore to work on a process plant, for example, that's generally a process by which somebody gets on a helicopter, gets to an offshore platform, and sometimes you can have, you often have many people making that journey. So if there is a way that we could reduce that, that's one way of ensuring that we're reducing our emissions. You could have a system whereby, instead of operators having to do all the work, you find a way of introducing more automation. And that ensures that you have less human interface and therefore less travel. And that also reduces emissions. So that's on the digital side. You also have ways of ensuring that you understand processes better and therefore can make them run a lot more efficiency and use a lot less energy. And that too is a digital method. So the solution has a digital leg. The other leg has to do with a non-digital area. And that's to do with battery storage. It's to do with decarbonizing technologies, such as renewable diesel. And I'll tell you a little bit more about that. It may be to do with methane detection, carbon capture, and so on. So those are some of the areas that we need to look at. So I'm going to give you a few examples of some of the projects that I've worked on that highlight, or some of them I've worked on, some of them I haven't, but they are projects that are taking place that have to do with some element of that. So in 2014, I was working on a plant. I was working on a project called the Concentric Gas Lift Project, and it was a way of ensuring that we could basically get gas out of wells that had liquid loading on it. So the liquid was blocking off the gas that we were trying to get out of the ground. And we'd been working on this for a while. I was the main engineer working on this, but I never had to go offshore. I was able to sit in a smart room, and I was able to communicate with a lot of people offshore, and we were able to get this done. So that's a very kind of low level. But the fact that the more companies are thinking of that as a way of reducing travel. But that's quite low level. We then also have the fact that rather than, I said I was talking to operators, but you could have a digital operator. So this example here is a good example of that. Can we get the sound, please?
Several hours a day, several operators will walk the facility, read gauges, listen for noise that doesn't sound right, look out at the horizon for anomalies, boats that may not be caught on radar, look for sheens, and so on and so on. So primarily right now, what we're looking to do with SPOT, or what we're doing with SPOT, is really trying to replicate that observation piece so that I don't need necessarily an operator to go do that. I can have an operator actually review that information from a central location, if you will.
So yes, I'm going to move on to the next one. Basically, what they're doing is they're actually getting this to work in such a way that these robots can actually see things that you and I won't be able to see, particularly to do with methane emissions. So that's something that is already kind of in place and is starting to happen. The other way, and for me, this is one of the most important aspects of this, if we accept the reality that in the meantime, it's hard to escape, whether it's making steels, whether it's pharmaceuticals, whether it's even trying to get hydrogen, blue hydrogen, or whether it's trying to design things that you and I need on a daily basis, we are still in a position where we will still rely on the use of fossil fuels. And therefore, one of the most important things we can do is carbon capture. And as I mentioned before, there is no way of solving the problem of climate change right now that does not involve some form of carbon capture. So let me do this very quickly, because I know time's fast spent. How much CO2 is there in the atmosphere? Quick answers. Very good, very good. How many trees are there on the Sahara? What was that? Did you say 3? That was not a serious answer, sorry. How many? Guess? Just guess a random number. What was that? Ooh. 100. 1.8 billion. And engineers from NASA were able to use artificial intelligence and the satellite systems to ascertain that just last year. So you do actually have quite a lot of trees already in the Sahara, and that's related to something we will talk about. Next one, which of the following places has warmed the most over the past 100 years? Is it Marrakesh, Basra, Vancouver, or Svalbard? I'm sure I've mispronounced that. That's it. Very good. And finally, who tweeted in January this year that he wants to give $100 million? That's good. Elon Musk, for anyone who didn't hear that. Very, very good. So in terms of carbon capture and storage, that is one of the most important things that we can do. And there are various ways of doing that. So you can basically have an underground cave system. We call it sequestration, where you take gas out of a process and you basically put it underground. You can also do the same for under the ocean, because you've obviously got a lot of pressure there, and it can be a very good trap for CO2. That, of course, comes with a few problems, including the impact on aquatic life, so that's important. You can basically get that CO2, and you can reuse it in various ways, like the ones that I mentioned here, soda, concrete, plastics, and so on. But the problem with any of these methods, particularly the reuse of CO2, is that these are not yet commercialized enough in order to actually solve the problem. You could also do a process by which you basically copy what plants do, and you encourage photosynthesis through the introduction of CO2 to water in controlled situations. You could store carbon dioxide in tree trunks, and so the reason I asked the question about trees in the Sahara is that one of the concepts that have been spoken about is that you could have a scenario where you actually plant trees all over the Sahara, and the hope is that you then get lots of that CO2 trapped in those tree trunks and roots and soil and so on. But yes, one of the things I was surprised to learn is that we actually have a lot of trees already, and the fact is we could have more. And you could also have genetically modified algae, where you basically get those to trap in a lot more CO2. You could use bioenergy with carbon capture and storage. But the problem, as I mentioned before, is most of these have not been scaled up. And remember what I said, that the role of a chemical engineer is to scale things up. So I'm going to skip this question just because of time. But there are a number of ways that we can capture carbon, but they fall under 3 key areas. So you could have a post-combustion removal. So basically, you already have this CO2 that's formed, and you can either use an absorber or an adsorber to basically remove those CO2s. And that is still one of the most commercial ways of achieving this. You could have a pre-combustion process. It's a process we call gasification. Oh, you've got the answer? Okay, so since you are the first to raise your hand, I will listen to your answer immediately after this. Thank you. So we got the post-combustion from the flue gas, and I take it most of you understand that flue gas is simply exhaust gas, right? You know that. Okay, so, and then you got the pre-combustion, you got a process called gasification, where you basically use fuel and oxygen, and you create a combination of hydrogen and carbon monoxide, and that's referred to as syngas. And not only does that provide you with a really good source of hydrogen, you can also use that through a process called the Fischer-Tropsch process to create a lot of other useful items that you use every day, and that can be a very effective way to do that. And you've also got oxy-fuel combustion, which involves the burning of fuel with oxygen in order to control flame temperatures, and so that some part of that is recycled into the system. So that's the oxy-fuel system. And so to summarize those particular systems, the oxy-fuel system, you can do that using these 2 systems here. So as I mentioned before, you can have an absorber, which remember I said was using a solvent, usually an amine-based reagent, in order to remove the CO2 selectively from the flue gas. You can then take that CO2 and you can direct it into storage, and that can be underwater or it can be under cave systems. That can then be transported and that can then be used. You can also have a system where you have something like activated charcoal, or you have molecular sieves, as I mentioned before, and those are then used to selectively take out the CO2. You can usually then use that CO2 to create a carbonic acid, and then you can then heat up that to remove the CO2 and use that in your storage. So that's one of the systems that you can use. And as I mentioned before, the ocean is quite a good sink for that. Here are a few examples of an absorption system that has been used out in the open. These are actually systems that are operating today. There's a company called Carbon Engineering, if you look them up. They've come up with these systems where you've got these cooling towers. You do have your systems inside it that are able to basically take out the CO2 from the air. You can then store that CO2, and that CO2 can be used in various ways. And that's by a company called Carbon Engineering. So this is an example of the system. So you've got this air intake. The air is drawn into these cooling towers. You then got a basic solution. I can see Professor de Knees there, so we're talking about chemistry now. And you've got your basic systems, and you were able to use that to create carbonate, and you can also then get the CO2 out of the system, and you can store it. You've also got another system, which is more of a sort of direct air capture. And that's using adsorption this time as opposed to absorption. And it operates in a way that your catalytic converter operates at home. And again, what you've got here is you have a system that can be regenerated. That system sits in a vessel or sits in your system. You collect the air that selectively removes the CO2. That can then be heated up and regenerated so that it can take on the next batch. You can take that CO2 and you can store it, and you can do a lot. You can do a lot with that. This has been done by a company called, I love their name, Global Thermostat. And Global Thermostat have done these with ExxonMobil, and they have it installed onto their systems. You've also got something called enhanced weathering, because what happens is very often when you emit these gases, they combine with moisture, they create acids. These acids fall onto rocks, and they actually get stored in the rocks in some form of carbonate. What you can do is you can create a system, maybe something like a quarry, where you have a number of these metals that are able to suck in the CO2. And again, this is still at a sort of very much a pilot scale, but it's something that is being worked on. This is probably my last quiz for today. So which was the world's first fully integrated industrial scale carbon capture and storage project? First one. Anyone want to guess? Yes. It sounds to me like if you just say Norway, you probably get the answer right. So yes, it's Norway. That was the first one. And the second question I'm going to ask you, because it touches on a different way of meeting our net zero emissions targets, is what is the world's simplest molecule and potential source of clean energy? Hydrogen, exactly. And what you can have is you can have these reformer units, and we often refer, you can have reformer units which are used in refineries, and you can use that to actually create hydrogen through the breaking down of hydrocarbons. And we often refer to that as green hydrogen. But you can also have a system where you basically take it out of water through electrolysis. And you can do that on a larger scale, and that is referred to as blue hydrogen. Unfortunately, we are not yet developed in that stage of producing blue hydrogen to a point where it can be scaled up. But that too is still going on. You also then have biofuels. And I would like to show you this. This is probably my last video. And this is a refinery in Singapore. It's owned by a company called Neste, and they are based in they're based in Finland, but they have the world's largest renewables refinery. And they produce something they refer to as renewable diesel. And I'll just show you a few clips from that.
For Finnish energy giant Neste, it is making a big bet here in the western end of Singapore.
Neste is already the world's largest producer of renewable diesel. Now it wants to fuel growth by pumping $1.5 billion in a new refinery here in Singapore, with a capacity to double production by 2022.
Effectively raising the stakes here to 2.6 million tons. So what exactly goes into generating renewable diesel? Breaking down the facts for us is Site Director Kenneth Lim.
We have more than 10 different kinds of feedstocks. So this, as you can see, is the animal's fat, one of the feedstock that we use. And we also have, for example, used cooking oil, soybean oil, as well as even fish oil, fish fat.
Where exactly do you source the feedstock from?
In the region, we source in Australia, and right now even sourcing from China and North America. So we have a global feedstock base.
I was given a tour around the high security facility.
Behind here, this is the pre-treatment facility process, which means it's purifying the feedstocks. All of the feedstocks we collected, all of the feedstocks are loaded on the pot. Behind it is actually the pot already, so everything is unloaded there and then moved to this facility, to this process.
After pre-treatment, the raw materials go to the refinery.
This is the next BTL process, which means it converts the purified feedstocks into the renewable diesel, and it is the patent technology of Neste.
So from here, it goes out into the market.
Yes, before it's shipped to the customers, we will do the test of the end product to make sure it meets all of the requirements from our customers.
The expanded plant will boost Neste's total renewables production to 4.5 million tons annually. And it comes out really clean and transparent?
It is. This is what it is coming out from the plant. So unlike the fossil diesel, renewable diesel does not contain aromatics, so it's very clean. You can reduce up to 90% of our carbon emissions compared to traditional fossil diesel. It burns very clean. It performs much better than the fossil diesel because it has a high cetane number.
CEO Peter Varnaker expects demand for renewable diesel to quadruple by 2030.
We see the regulation also changing in especially Europe. I mean, Europe is on the forefront. So there is a new regulation that is being put in place. I mean, it has been voted on the European level, the so-called RED2 regulation, that is now being adapted by the member states. And that sets clear targets, mandates, and what needs to be achieved in terms of greenhouse gas emission reductions. The same is also happening in the United States, especially California being on the forefront, but not just limited to California anymore. Also some other states are setting clear regulations and enforcing mandates. Due to the regulations, there is the need also for products that are helping to reduce CO2 emissions on the planet.
So I'm going to say, so this is my last slide, I believe. So what is the future of chemical engineering? So certainly it's in those areas. It's in the carbon capture. It's in the chemical engineers who work on the models for ensuring that the CO2 can be transported to the places that use them. It's in the scaling up of some of these very innovative ways. And hopefully at that point, we eventually get to a point where there is no need for any use of fossil fuels, and we can have this future that we leave to the planet, and particularly to people in the global south, a world that's fit to live in. So that's the end of my presentation. Thank you.
Thank you very much. I think if we're quick, we should have time for 1 or 2 questions. So if anyone in the theatre has a question, you can head to the microphone. And in the meantime, I will ask a question from the Hoover app, so from our online audience. Dami from Ireland wants to know, is there a fear that renewable energy sources may not be as reliable or efficient as fossil fuel energy?
There was certainly a concern at the start. But I believe that we've actually come a long way in the development of renewable sources. And, a number of things are happening. We're becoming more efficient at producing renewable energy and becoming more efficient at storing it. And sometimes, and that has often been the issue. But it is also a valid concern, and it's one of the reasons why a sudden switch, I keep hitting this poor mic, but a sudden switch to renewable sources without that sort of transition process can actually be damaging to the overall cause.
We will now take a question from the theatre, so if you'd like to step forward.
Hi, I'm Eslem from Spain. I wanted to ask about the renewable energy sources. So how do you think investment should be divided for the modern sources of renewable energy and the traditional sources of renewable energy? So which one would be more better for the well-being of the planet and for humans as well in the future?
Yes, so I think we have to think about that in a more holistic sense, and almost rather than sort of say we're going to focus more on this than the other, I prefer to think about it in a holistic sense. So can we ensure that we can maintain smooth energy supply and make it affordable, particularly for the world's poorest? Can we also ensure that that energy that is being produced, any impact that's coming out of that we are able to catch carbon dioxide that's produced, catch these emissions, store them, reuse them? And can we also, in that process, spend, and I would say that obviously we should be investing a lot more into ensuring that those renewable sources renewable sources can be invested in to ensure that they're more sustainable and more affordable. So in one sense, I'd rather look at it in a less binary way of this or the other. I tend to think of it more of how do we get to that point of net zero? Because that's where we're all kind of trying to get to. But how do we ensure that we do not kill off the planet in the process? So I hope I've answered your question.
Thank you.
Thanks.
And I think we'll just have one final question from the Hoover app, which is from Carson from Hong Kong, who asks, as a consumer, what should we do to aid the energy transition?
Fantastic. That's a brilliant question. And do you know something? If you and I, every time, and I know this sounds almost silly and basic, but if every time you turn on the kettle to have a cup of tea, if what you did was put in just as much water as you need, rather than fill it up every time, and I'm a massive hypocrite for saying this because I tend to do that all the time. If we all did that, you would be doing a massive effort in terms of reduction of CO2. There's also what we can do as a community. So one of the main things that's driving this change is not because people in oil and gas companies have suddenly had a road to Damascus experience. It's the consumer that's driving this. And it's the fact that you have what you call stakeholder, shareholder activism that is actually really driving those changes. And that to me is one of the most important factors. So there is always something that you and I can be doing in terms of making our voices heard. Because the bit that I haven't spoken about here is the policy framework that underpins anything that's happening. You will get acceleration in the areas that you want to get the acceleration in if the legislation can be made to, can be forced in that direction. But if it's all still very loose, if you still have governments like some governments, who I won't mention, who are very even skeptical about climate change, then you might have problems. I won't say that it's Trump I'm talking about.
Brilliant. So there's some small steps that we can all take.
Yes, that's right. That's right.
So thank you very much. That's all the time we had for questions. So
that took a bit long.
That's all right. It was very interesting, so we won't fault you. And I will call on Noga to give the vote of thanks.
Dear Dr. Ollie Folayan, young people, such as those in our audience here, have never been more involved in the fight against climate change, and the move towards clean energy, as we know, is a key in that fight. Your lecture this afternoon introduced us to the role of chemical engineers in the energy transition goal and in the world. There is no shortage of obstacles in the energy transition, from balancing clean energy development to meeting the world's energy needs today, and to more practical obstacles such as tackling corrosive gas wastes in plants. However, with your lead and with international collaborations, I am confident that a future with clean energy and better energy management is on the horizon, and perhaps a future with some newly aspired chemical engineers in our audience here. For me, growing up, the term chemical engineer was synonymous with intimidating genius and definitely didn't spark inspiration like the evil genius in your book from your childhood. However, today, your use of metaphors and examples showed me that engineers are simply problem solvers wearing many hats and creating a world that never has been. Your inspiring and engaging lecture this afternoon has been a celebration of science for humanity, our theme at the forum this year, and it has been an incredible honor to have you with us today. So on behalf of all of us here at the London International Youth Science Forum, thank you.
Thank you. Thank you for having me. I haven't forgotten that somebody had an answer for me, so I'll find out from you, and you'll get your prize. Thank you.
Thank you very much. BEng, this is just a short announcement. Okay, you've got about 20 minutes now just to stretch your legs, get into the park. We need you back outside for this afternoon's final lecture at 10 minutes before 4. But otherwise, thank you very much, and we'll have the first row leading out, please.